Okay. So today we will study digital certificates mainly and revise about digital signature. Okay, because in last class we couldn't complete this topic, so I thought we'll start from beginning and we'll complete this. Okay. All right. I will just switch off video of mine. Please feel free to ask me a question if you don't understand anything. So these are the references I have used. Uh, this is a lovely course, online course available by Dan Bonnet of Stanford. He's a very famous Stanford prof. Uh, and I strongly recommend to at least go to this website. This online course available also in Coursera for free. And it's lovely course, right? However, it is only on cryptography, but very lovely course. You know, you will enjoy going through it if you get time to go through it. So these are topics we'll cover. We'll try to cover most of these. Okay. So now we are towards the end of cryptography journey, right? Okay. And next class we'll finish it and we'll revise what we have done so far. So what we have started with is we started with symmetric encryption, AES, DS, modes of operation, and these are the properties we could achieve. And then we have seen that cryptographic hash function, which is a hash of a big piece of data, for example, a file, we can create a small hash. Okay. So now this hash represents uniquely this file or data, whatever. Okay. So, and we found that although it may not have many properties like confidentiality, authentication, non-repetition, but it's very useful function in cryptography because we are using this in association with many other functions. For example, Mac by itself has is not very practical, but we combine Mac and hash, then it becomes very useful, right? Like here. So now important part of Mac we have seen is integrity and authenticity, provided sender receiver have the secret key. But none of these have non-repudiation property. What is non-repudiation property? Then Alice and Bob, when they are sending a message to each other, they can, in symmetric key encryption, they can fool each other, right? They can tell lie. And if Alice goes to police or somewhere and say that Bob has fooled me or sent, you know, instead of giving $100, he has just given me $10. There's no way for police to implicate Bob. Okay, so basically, it is very difficult to find out who is telling the truth. Okay, now this non-repetition property we want to achieve, and we have seen that even our asymmetric encryption, we cannot have non-repetition property. Okay, now digital signatures is the only way to have non-repetition property. Now, for example, when you give a check to somebody, okay, saving banks check, you sign at the end, right? And if you don't honor this, if you don't have money in account and then receiver deposits this check in the bank and is dishonored, then you will be asked by court to pay penalty, or maybe you will be penalized for that, right? So anybody who has check with your signature can go to the court. Now, property of the signature is that it's very small in comparison size of the check, okay, and is unique depending on each person, right? It's very difficult to fake it because your hand, you know, I mean, there's a important property, okay, and however, we cannot replicate this as it is in digital world because ultimately everything, you know, this thing is nothing but sequence of zeros and ones. Similarly, sign is also zeros and ones. some combination of zeros, one, right? So I can always create any document, then any document, check the, change the values in check. The document can be anything, and then attach this signature, right? So we cannot copy this model of physical signature. So we have now digital signature. Now the important thing that we will of course try to solve is that MATM attack, man in the middle attack, is possible in public keys, right? And for that we also need digital signature. Okay. For example, when Alice wants to communicate to Bob, okay, using asymmetric key encryption, then Alice needs Bob's public key. Okay, like RSA algorithm, I mean, if you remember, Bob sends his own public key, PK, and Alice uses his public key to encrypt message M, get ciphertext C, and she sends it to Bob, and Bob uses a private key, right? So this is the mechanism. But now this public key that she uses to encrypt, public key of Bob, how does she know this is genuine? It's not fake. Okay, so what may happen is that Mallory in between intercepts when the communication of public key is happening between Bob and Alice. Mallory in between intercepts a message from Bob where Bob sends public key, and then Mallory changes or this key by, or Mallory sends instead of that her own public key. Okay, so it's very simple. It's we have discussed this in last class also, right? So Bob generates public key and private key and sends public key to Alice because Alice might have demanded that, and then this is the normal process, right? Okay. So what may happen is that, sorry, yeah, I'm so sorry. So this is the normal process, but actually what now Mallory can do is as follows. She intercepts this public key of Bob, which we call PK Bob, and changes it by her own private public key. Now Alice receives the public key of Mallory, and she doesn't even know that this key is coming from Mallory. Okay, and she signs this message, or she sends this, encrypts this message using Mallory's public key, thinking that she is using Bob's public key. Mallory decrypts this message using her own public private key, and then encrypts again this, changes this message to M dash, and encrypts this with Bob's public key and sends it to Bob. Okay, what Bob's receive is malicious message. Okay, so now why is this happening? Because Alice is not getting genuine public key of Bob. Okay, now assume that, do you think this is a very unique scenario, or you're not using public key for encryption? Do you use public key for encryption and everyday tasks that you do on your computer? Anyone? Yeah. Archita, I can see your name here. Can you answer this question? Archita, are you there? Okay. Anybody can answer this question? Do we use public key of somebody? How does your browser work? Yeah, go ahead.
So for deciding whether the transaction or whether the message was sent by that particular user, we can use public keys.
Yeah, but I am asking for the application, right? You're right. What application? Your browsers use, right? Public key? You are communicating with, for example, Google or Amazon.com. Okay, you want to send, say, session key to Amazon.com, and you use RSA. So you are going to use Amazon.com's public key. How do you know this public key is genuine? Right? Of course, there is a mechanism that's called certification that we'll read afterwards, right? Okay. So we very often use public key and private key because key exchanges, have you seen, whenever we do browser communicates with server, say Amazon.com server, and a lot of information is coming from there, and you cannot use asymmetric key encryption. You cannot use RSA. That we have seen, RSA is inefficient. Yeah? It can send only very small message. Okay. Then you have to okay. So in the beginning, you'll have to you have to exchange symmetric key or session key using RSA. So for that you need receivers, that is Amazon.com's public key. Yeah, all right. Okay. Okay. So digital signature, again we have seen that. Now here in this one, the signature does not depend on the content. Okay, and that is the reason even on physical checks, frauds were very common. Why? You know, you use change this $1 to $100. You can do that. You can create, because you know, use some kind of eraser and then rewrite it, and used to happen. Okay, but if this signature depends on the content, then you cannot do the fraud, right? This is exactly what we do in case of digital signature. This is a file. Don't see this as a physical check. This is a bit set of, this is nothing but series of bits. Okay, it could be anything. It could be a document. Okay, you take this document and use encrypt it. Say for example, you are using RSA or maybe elliptical curve or one of these methods. Okay, and use, say for example, Alice is sending to Bob, use Alice's private key for encryption using RSA. Okay, so you are using private key now for encryption. Okay, and that's called signature. Okay, and it goes to Bob. Bob will receive both this thing and also signature. So original document and signature. Now he does not have a private key of Alice, so he cannot create signature, equivalent signature. So what he does is that he takes the signature and uses the public key of Alice, okay, and decrypt it, and as a result he gets the original document. So he compares this original document with the new document that he gets, or original message with the new message, or M dash we can say, and then if verifies, then done. Okay, all right, simple. So what we achieve through this authenticity, integrity, and non-reputation. Why non-reputation we are able to achieve now? Because everyone has a public key of Alice, and only Alice has a public key, private key. Only Alice has her own private key. Okay, nobody else has a private key, and she has signed with that private key. Now she is liable for whatever she has signed for. Okay, now these keys, private keys, cannot be guessed because it's you know, random number. Is a random number, right? It's a 1 out of 10 million, 100 million, or more than that, few billion, right? Randomly picked up. So it's not that she can say that somebody else has got this, uh, has created this, you know, secret signing key which is same as my key. She cannot. Okay, all right. Any question? So digital signatures are a symmetric way of providing integrity and authenticity. All right. Okay. All right. So what with the
So,
digital signature? Yeah.
are the private keys like unique for each user? Like, for example, say if the sender is communicating with multiple receivers, so for each receiver there will be a unique private key, or they will have a common private key for the sender.
You tell me. We had one example in the last class, right? See, public key is no is public key is public, known to everyone. Okay, now it depends on the application that we are, right? If it's a one-to-one, then private key, see, Alice will generate private key, use it for some time, and then possibly after that can be discarded. So it totally depends on the application. If Alice is a server, Alice is basically a server, for example, and distributing software to everyone. You've seen that example, right? This is a
Yes.
server and is sending the software to everyone. So all the users will have, and that software she has signed with private key, say SKLS, and then we got signature. Okay. Now everyone can, and this signature is available to everyone who has downloaded or who has got this software. What can they do? In this case, they all have same public key of Alice. Okay, so now using this, they can verify the signature. All right. Otherwise, it can be one-to-one, depending on the application, right? She can also generate. Can she generate multiple signatures? For different set of applications, she can always generate, right? If you have multiple browser, for example,
No, then if like we can change the key, so how will it again ensure that that key which was used to sign the signature, like the signature, was generated by the sender only?
no. So basically, what is the probability? See, this key, or private key, is randomly generated, right? Pseudo randomly generated. Is a random number. Okay, got it? Okay, it's generated
Yes.
out of what? Is one of the 2 raised power 2048 or even more than that. And this is, if you go to Goa, it will have less number of grains of sand in Goa than this number. So probability that two user can pick up the same key is 1 in 100 or billion, or maybe 1 trillion or something like that. Okay. So only
I will
she,
say like,
and public key is corresponding to this private key, which everyone knows. Okay. Yeah, go ahead.
can
Yeah,
it
yeah.
happen like when we use the key once and then after sending the message we then like discard that key? So how will we ensure that the key which was used to sign that message was generated by the sender only?
Yes. So you'll have to, there is some lifetime that you have to be defined. There's always time stamped and lifetime, right? For public key. So you may have to discard it, right? I mean, maybe private key is lost or private key is leaked, right? Then you have to get new private key. So again, it depends on situation and so on, right? So as an exercise, you find out what is in general lifetime of a private key, public key. Just Google it, you will find it out. Huh? Okay. Any other question? Very good. I am happy that you asked question. All right, shall we move ahead? Okay. So now characteristic of digital signature is that it's authentic, it's unforgeable. Unforgeable means recipient Bob can prove to someone that Alice and no one else must have signed document. It is only Alice who has signed the document because only she has the private key corresponding to this public key. Okay, it's not reusable. It means that there is a document and you get the signature. You can't put this signature into another document. This this is message 1 or this is message 2. You cannot put signature corresponding to message 2. Okay. Signed document is unalterable. You know, if you change this document, okay, somebody, right, in between Mallory gets this document and changes from M1 to M1 dash, but she cannot change the signature. At most what she can do is that create some fake signature. Okay, but only genuine signature can be created by Alice because Alice uses her private key, right? So when Bob receives this, he will get the this message or document, and then this signature, and then it does the verification function and both match. Okay, then you know, for example, he calculates the hash of whatever, and then both match. Then using, of course, he has to use public key of Alice. Then he knows that everything is okay. Otherwise, there's something fake. Signatures cannot be repudiated, right? So it means the signer cannot later claim that she didn't sign it because she is the owner of the private key and whose public key is known to everyone. Okay. Of course, signature has to be bit pattern. And also, you know, performance has to be good because digital signature should not take time. And it will be relatively easy to recognize and verify digital signatures. Okay. All right. So now let's again look at what we have studied earlier. So we of course use private key. Okay. And the originator, that's Alice, sends both message and the digital signature. If she sends only digital signature, it's of no use, right? Because then Bob cannot verify it. Because the digital signature is based on the message. All right. So basically, digital signatures verifies the origin, that's Alice has sent it, and the integrity. If the document is changed, then one will come to know about it. Or if signature is changed, then even then Bob will come to know about this, right? All right. So this only the owner of the private key can sign the message. This we have already studied, and everybody can verify the signature with the public key. Whoever, so Alice has signed a message with her signature that uses the private key of Alice. When this goes, so now note that there is no confidentiality here. So everybody can see that whoever has PK of Alice, public key of Alice, can verify this. Okay, all right. So basically, it has 3 steps. Digital signature has 3 steps. First is key generation, SK and PK. So Alice generates public key and private key. Okay, and then she signs message M using her own private key, and that's a signature. She sends signature along with message to Bob, and Bob once received this, Bob has a public key of Alice, then can verify this. Okay, so these are the 3 properties: correctness, efficiency, and security. So it's the same thing that's depicted here. So I will skip this. Okay. Now this is pictorially again I'm trying to discuss the same point here. The Bob has a message M. Now here it's changed Bob to Alice, not Alice to Bob. Okay. So Bob wants to send something to Alice. So Bob has a message M. He uses his own private key and okay uses the algorithm, say RSA or whatever. Okay, and creates signature S. Now this along with the message, this original message, he appends to this signature S and both go to Alice. Now what will Alice do? She will look at the message, this message, and get the signature. Now obviously she can work only with the public key of Bob, and she does whatever she wants to do on signature part and then compares both and finds out the valid signature is valid or not. Basically she applies public key, do the decryption on S using public key. Okay, and get the original document back, original message back, and compare the a message M dash, and which is if same as original message, then everything is okay. Now this method is little long because here the if message is large, then signature will also be large because it's almost same size. Okay, so now we want to reduce the size of signature, so we can use hash. So now it becomes something like this. Original message M, Bob has to send to Alice. Now first he does is that he gets a hash of M. Okay, and then in hash of M or H of M, he encrypts. Now this is a small size, right? He encrypts with his own private key, and now this becomes signature. Okay, now he sends both M and S signature to Alice. Alice receives the both. This is M and this is the S. Okay, now Alice applies same hash function here and gets H. So this is H of M. Okay, and then signature she applies a public key, and as a result of that, what she gets is H dash. If both H and is equal to H dash, then signature, it verifies the signature. Okay, is it clear? Any question? All right. So now as a result of this, we can get non-repetition and authenticity. Now message goes in plain text, so it's non-confidential. Okay, all right, please go through this. This is, you go to this link, then you will find out details. Okay, so this is all about digital signature. Now we have yet not solved the problem of MITM, where when Bob sends a public key to Alice, in between and Mallory can change that, right? So now, yeah, question. Okay, so now in order to prevent MITM attack, every participant can verify the authenticity of other person's public key. When Alice received public key PK of Bob, she must verify that this is genuine and correct. This is the original public key, right? What is the way she can verify this? Okay, we use this method very often, right? Okay, you know, there used to be something called, nowadays it's not in use, but something called character certificate. Have you heard this? When you go from one school to another school, especially the principal will give character certificate. This guy is good and so on and so forth, is bright and good in sports and all that, right? And then you give this certificate to principal of other school or admission committee, and they will accept your possibly your application. Same thing happens also when you ask for recommendation letter, right? For admissions abroad, what is the use of recommendation letter? They, you know, I mean, there are thousands of schools in US or Canada or wherever, and then they want somebody to vouch for you. There's a possibility that you would have possibly faked your transcripts, some possibility. Okay, but if then there is another, but somebody has to say that no, this guy is good. So they require letter of recommendation, right? So in real life, we can use, you know, driving license. Alice can send to Bob, look, I am genuine. Okay, here is my Aadhaar card or driving license. So that may become certificate. Or Bob can send it to, Bob can send his own driving license and say that now look, see, my name is Bob, and you can see it's there in Aadhaar card. Okay, all right. So there is a need for web of trust. Somebody must vouch that Boss public key is genuine. Okay. Now question is that if you know, at least if you have a classmates and then you are communicating, you know each other, right? So you can trust each other. But in this world, in world of internet, there are number of devices, IP devices that use internet is more than the number of people. Every person has 3-4, you know, machines and IP address and so on. So how do you trust billions of people or machines you have never seen? How do you know you are communicating with a machine, and that machine's public key is genuine? Okay, so now somebody should say, look, you are communicating with Google, you know, when you are communicating with google.com, then Google will respond back to you when you ask for public key, not only his own its own public key, but also a certificate from third person that this guy is actually Google. It's nothing but letter of introduction. Okay, so what we do now, we have a trust anchor whom we can explicitly trust, and we call them as certification authority. Okay, so now we have a concept of CA, a certification authority, and they are responsible for verifying the identity of users. Like, you know, I mean, one particular example is could be, you know, possibly I have given this example to you guys, maybe may not be. How do you, when your father got married to your mother and both are from, and there was no, what do you call that, matrimonial, what do you call that, apps, you know, whatever, Shadi or Viva.com or whatever, and no dating app also, right? What dating app nowadays people is, I don't even know, is something. Okay, so what was the way? He possibly has met your mother, or mother has met your father for the first time, and they agreed to get married, right? So there must be someone common, maybe your uncle, you know, father's uncle, aunt, or you know, second cousin, third cousin, or somebody senior in that village or whatever, would have said, you know, I know both parties and they are good. Okay, they will vouch for, so there must be some grandfather, or you know, some what do you call that, head of village will say, I know both Bob and Alice and both are good. So Alice says, okay, I want to marry, Bob says, I want to marry Alice, but I don't know her. So somebody will say, okay, I know her and she is good girl. Okay, so same thing is happening here. Somebody has to vouch for both Alice and Alice's public key. Okay, and this is called role of CA. So the question is that how many such people can be under a CA? If there can't be one single person in whole India who will arrange marriages between people. There can be billions, there can billions of Bobs and Alices, right? So that person cannot do the job because CA can handle only certain number of people, okay, certain number of devices, right? So okay, before the going to that, and that problem is solved that we call PKI, public key infrastructure. Okay, it's not one CA per multiples of CAs, right? And they are connected in some way that each one trusts other person or other CA. Okay. Okay. So now we come to the concept called digital certificates. Okay, it's application of digital signature, right? Okay. So who will issue a certificate? Somebody. CA will issue a certificate about say Alice and Alice's public key. Okay. So mainly about the public key. So is a document that proves the ownership of the public key mentioned in the certificate. So digital certificate is signed by CA who certify the ownership of contained public keys. Okay. So basically it's endorsement of someone's public key. So a certificate contains at least two things: identity of a person and the public key. Okay, it will be Alice, for example, and Alice's public key. All right. So now there is a standard called X.509 because everything has to be standard based. Otherwise, the certificate will not be trusted by anybody else, right? So that defines this kind of format. Okay. Say what is the version number of the certificate? What is every certificate will have serial number, right? Okay. What kind of algorithm is used for signing? What is the period of validity of the signature? What is the name of the subject? For example, Alice here. Then the public key of Alice, etc., etc., and then signature on some of these fields. Okay, so whose signature? This CA's signature. Okay, so the process is as follows. Okay, you please go through this. I am not going to cover this. Okay, this is about the detail what can be different fields in this certification. Please go through it. It's very simple. So Alice wants to get a certificate. She requests certification authority. Certification authority will say who are you and ask all the questions, and then she replies that all that, and then she sends her public key to certification authority, and then certification authority issues a certificate. Okay, and that certificate, when Alice communicates to Bob, okay, she sends the certificate issued by certification authority. Now, so certification authority issues certificate is nothing but the contents of whatever Alice has submitted, a digital signature on that. So certification authority uses its own private key to sign, and certification authority's public key is known to everyone. So when Bob receives this, he can look at the certificate and decrypt the certificate using certification authority's public key. And then he will get inside public key of Alice. Okay, so basically 3-part algorithm. Okay, so first thing is Alice has got to, get digital certificate from CA. Okay, So users are aware of public key of CA. This is assumption that both Alice and Bob know the public key of CA. So PK of CA is known to everyone. Assuming that there is only single, only one CA in that area. Okay. Before communicating to any other user, each user needs to communicate with CA and obtain a digital certificate of their public key. Alice sends all identification information about her to registration authority, and that captures and authenticates the identity of the user. So Alice's identity she has to prove to CA, and then Alice generates private key and public key, and then submits a certificate request to the CA. Please give me a certificate. Okay, and CA authenticates the public key submitted by Alice and computes hash of Alice's identification information, her key of her public key, and CA's identification, and sends that certificate to Alice. So, okay, so what he does is that he takes only few fields from this request and creates hash of that and signs that with his own private key. Okay, all right. So now we can look, and then when the part 2 is that Alice sends that to Bob. Okay, so Alice sends her certificate to Bob. Bob decrypts the certificate using public key of CA and extracts the public key of Alice. And now public key of Alice is available to Bob. They can do communication with each other. So this picture depicts the process. Okay, look at very carefully. So Alice gets this certificate. Now many fields are omitted in this one. So just be just look at this, right? Okay, so this is Bob here. Bob requests for a certificate of his public key. Okay, so this certificate has these things in plain: Bob's ID information about Bob, Bob's public key, and the CA information. CA information is also known because this can also be verified, right? And now what is done in order to create certificate, this information, what CA does is that he will, or it will do hash of this information. Okay, so this is hash, and then encrypt it with his own public private key, CS private key. So SKCA will encrypt, and that becomes signature. Note that signature size is small because it's a hash of this information. Now Bob sends this to Alice. Okay, all right, this certificate. So what Alice does is that she will look at this part, plain part, and will do hash, because hash function is known. We'll get this hash of this part. Okay, and then she will take the signature and then decrypt it using CA's public key, which is PK of CA, and we'll get this one, and if she will compare both and both match, then signature verifies. It means that now the public key that she has received here is correct. Okay, got it? Any question? Any question up to this point? Now certificate, note that certificate contains a lot of information in plain text and then hash of some information which includes public key. Okay, when recipient receives it, then all he does is that he looks at the certificate, decrypts it, and compares it with hash of whatever he has received, and both match. It means that now whatever he has received, all this information is correct. Okay, now this says that what CA should do before issuing a certificate, right? Should all these checks CA will do before issuing a certificate. Okay, all right. Please go through this. So characteristics is that no party other than certification authority can modify the certificate without being detected. As we have discussed earlier, that certificate also has a lifetime. Okay. So this protocol X509 is used in IP security protocols, SSL and TLS, like your HTTPS uses TLS, right? Your browser uses HTTPS, is nothing but uses TLS. So it means that now this digital certificate with the method or protocol X.509 is being used. So very commonly heavily used protocol. Okay. Now how long certificate should be valid? Can certificate be revoked? Yes. What happens if certification authority messes up and issues wrong certificate? Okay, then it can also be revoked, or certification is stored in, Alice stores certificate of her public key in a card, smart card, and card is lost. Then it's required. Okay, or it could be many other reasons, right? For example, but Alice has been issued by somebody, CA, some certificate of public key, and Alice leaves that company. Okay, then that certificate has to be revoked. Or somebody has been given certificate and a person dies, then certification has to be revoked such that nobody else can use it, right? So so one technique of that is called CRL, certification revocation list. So now you can see that CRL is being issued very often by whom? By CA, organizations of CA or PKI, right? And basically a browser keeps getting revocation lists from some central entity, and then it learns from that these public keys are invalid. All right. Okay. So what we have studied today, digital certificate is signed attestation of identity. Certification binds the identity of user to their public key. If an untrusted network in an untrusted network, intruder can show its own public key okay, just leave it something incomplete. Okay. Okay, there is a need for trusted third party that can vouch for public key of station or a person, and then we use CA for that reason, right? CAs provide trust, right? CAs are most trustworthy person because everyone trusts that. And then next class we'll see that these CAs are interconnected, and there is something called root CA. It's like most important person in the organization, CA organization, like. So it can be, it's a kind of tree, and trust comes from root CA to first level CA, second level CA, and so on. Okay, any question? Okay, so we have a class today from 7 to 8.